Today we're going to try and parse a billion rows in Rust in under 10 seconds. So there's kind of an old challenge that's right here. We're basically trying to parse a billion rows of this example like weather text where you have like a city and an observation. And you basically want to find the min, the max, and the average for each city. The problem is this file is like 10 gigs big. And so some of the repos are here for the current leaderboard. Some people are doing it in 1 second. With Java, surprisingly. I'm going to aim for at least 10 seconds. I think we can do it pretty easily in one stream, and then we're just going to try to laser in. I think we can get down to probably like 4 or 5 seconds, maybe even 2 if we really go hard. Yeah, so basically it's just this massive file, and then we produce an output like this. And of course we have to make our output matches, and there's some other important, interesting bits here. So actually all of these values are floats, but they have only 1 point of decimal precision. So what I have right now is just a very naive implementation. It's basically as simple as I can go. And so I've set this up to run via cargo bench. So I'm just going to run this in the background, and it's going to kind of record the time for our first bench. I'll show you the harness in a second. But basically this is as simple as I could go, right? So we just hard code the paths for the measurements, right? This is, if I actually grab this path, home Troy, Java, you can see, yeah, this file is massive, 14 gigs. And so this, the expected, is basically this here in the README. I don't need to show you that. We read everything in, run the solution, and then format everything and see how long it took. And solution's pretty simple. We just basically read the whole thing into memory, which is kind of insane. Like if we look on htop right now, yeah, you can see we're using quite a bit of memory because we have that whole file loaded in. So we're definitely going to want to change this, right, because we're only reading through it sequentially, like a single time. And so we just run through each line, split it, do the parsing, a lot of unwraps. This, this is just simple code. And then if we have a station already, we basically update min and max and then add to the count and the average so we can average it. Otherwise, we push a new one with temp as the min, max, and the average with only one thing. And then we also have to sort them by name, so the output's the same. And then the formatting is basically what you'd expect. It's just the name equals and then min, average, max. And then we do the comma space if it's not the end, just like here. Yeah, and then this test basically just uses pretty assertions to make sure this still works. And then we're running this right now with cargo bench. And so the test harness looks like this. You can see we're basically, it gets a little annoying because this right now takes about 3 minutes to run, right? So we can't just pump this into something like Criterion because it wants to iterate on it and find like statistical convergence on how long the test actually takes, so it knows how long it runs for. The problem is, obviously, we don't want to sit around and wait for an hour for it to do like 10 iterations of our benchmark, and eventually we're going to want to use all the cores, so we can't even run these in parallel. So basically, I made a custom simple thing just because it's like a one-shot benchmark where we don't really care about statistical significance. We just want to see how fast we can sort of get this, in a general ballpark. Really of just numbers from the starting number, right? So this will be about maybe 200 seconds. If we can get 20x faster than this, I'll be happy, and I think that's very doable. And yeah, so basically we just run some git commands, get the hash, compare the measurements. It's almost the same as this runner here in this test, right, where we basically run it. And then we try to open this JSON file, which right now we don't have. I'll show you this in a second when it's done. But so because we don't have it, it's basically going to create a new empty vec and then push to this. Oh, okay, so it took 155 seconds. That's not too bad. And then this is the commit. And so I just cat out. Oh, shoot, our tree was dirty, so the results won't be saved. What did I miss here? Oh, I put a new line. Oh, that's funny. Okay, sorry, guys. We got to redo this. But basically, I'm trying to do this so it'll be somewhat official, right? Where we basically can commit our change. Because we're only doing one-shot benchmarking, we can't have the auto thing from Criterion where it tells you if it got faster or slower. And so basically what we need to do, because it's one shot, is record this file of the rev of what our code was with the actual time it took. So yeah, I'm just going to fix this real quick. We'll just get rid of this, make sure the diff is gone. Okay, so yeah, basically this is the starting point of the trivial code. And then while we rerun this, I'll kind of talk through like what the first stages of optimization are. But let's go ahead and get our bench, whoops, let me just double check, okay. Get our benchmark here without messing with anything. Okay, so, yeah, we kind of went through this briefly. The first thing we're going to want to do is, wait, when do we check if, Okay, this is the first thing we do. So if I start modifying it now, it should be fine now that we've started running it, which is probably how we're going to do this because we're only using one core right now, so it doesn't matter if like Rust Analyzer is running in the background. So we don't actually want to read this into one massive string. I'm thinking the first thing we do here is we want to use mmap. I think there's a crate for this. I think there was like a forked version, yeah, memap 2. Okay. So yeah, it looks like you give it the path and then it gives you back this. Ooh, okay. So yeah, we're definitely going to want to use this memadvise and say sequential, right, because that's how we're going to read it. Yeah, so let's get going with this guy actually. Mmap 2. Let's just go in here real quick to, what's it called? Here. I really hope it doesn't cry about my tree being different now. That'd be funny. Do they have an example we can just steal from? Oh, beautiful. Okay. Yeah, so instead of doing this whole read a string business, we're just going to do this. And let's copy their imports too. And that's going to be awkward because down here we're using we have to have this trade in scope to write to the string, so we might have to change that in a sec. We can do error handling later because really none of this stuff should ever fail. And we need to keep the path actually, which, oh yeah, we passed that as a parameter. Easy, okay. So instead of readme, we're just going to change this to be input path to unwrap, and then this probably is like a deref as bytes or something. But yeah, you can see we got the results now. So basically it's this simple format I showed you guys, where you just have the rev and the time, and we basically just save a vector of that in and out of this file. Whoops. And so, yeah, you can see this. And so we only save it out if the tree's dirty. So actually, if the tree is dirty, we want to exit with an invalid code to basically be like, hey, you got to commit and then run this. So basically, at every stage as we're changing the code, we can have like an official idea of where we're at. Mmap. Let's see, can we like deref this down to bytes or something? No, we're gonna have to. Oh no, that does look like it works. Okay. Yeah, we don't want to return the whole thing into a string because we want to be able to use the MMU to kind of stream through this. We could probably split this at newlines, but it probably needs a byte string. Oh, is this always? I guess it's always a closure. This has to be a byte here. Okay. Okay, so then we want to do from UTF-8 of bytes. Yeah, eventually we can probably use unsafe to get rid of some of these bounds checks and like UTF-8 validation. But yeah, so it looks like this should work. So I run cargo bench. What are you crying about? Okay, so yeah, it's because the tree's dirty. So basically, it's forcing us to commit every time. So that's probably good. Except now we're getting trait errors. Okay, we can just use this right here. Huh? We already do this at what? Oh, duh. We have to use it for both. Okay, compiles, so we can commit this. And so this is mmap input file. Now we can bench this. And my predictions for this first one. So before, basically, we have to allocate all this memory, do all the I/O at once. Now this is streaming, and the look ahead should be able to help us as well. So I'm going to say this is going to speed it up by like I/O bound is usually something high. I'm going to say this is going to speed it up by at least 50%. So I think this should take around 100 seconds or so, is my guess. Okay, and then so while that's running, we're going to find the answer to that soon. But we can actually start on some of the next optimizations I want to do here. So what else can we do? I'm thinking actually we can make these, we can all switch these to sign numbers. Actually, can these ever be negative? Yes, okay, one of them is, one of the mins is. So if we just make this, and we want to probably make it small too, so it's more likely to fit in our cache. And so these are negative, I think it's only negative 100 to positive 100. So we could literally just do I8 for all of these. And then the average has to be probably an I32. And so instead of parsing this here, we're actually going to parse so this is going to be temp string, and then we're actually going to split that again into temp int and temp decimal, and we're going to split this by the dot. I think let's just hope that the format in here is all the same. And we'll just print it here, just in case that happens. Hopefully it won't. Okay, so now we have basically the parts of this, and so this temp is now going to be an I8, and this is going to be, oh, I probably going to parse these now. Okay, and so if there is a negative sign, right, there's no examples, but it should be after the semicolon but before the dot. So yeah, this parsing should work. And this is going to be temp decimal. Oh, let's make this consistent. We'll just do TMP, a little shorter. The problem is it's like temperature and not temporary. Actually, let's undo this. Decimal. Okay, so then the actual temperature is going to be temp int times 10 plus. So actually these are kind of off by, okay, this is going to be 100 more than what we should. Temp int temp. Okay, and then this is going to be as I32. Ooh, interesting. That's not good. Ooh, it's probably something weird with this. Is there like a stray new line at the end of the file? If we 50. Okay, there is a new line at the end. So, we literally, that's funny, we ran literally the whole thing and then it didn't work. So what do we do here? We've already modified this, so did it finish? Oh no, it failed. Yeah, okay, this is only from last time. So we're still working on this. I still want to log what that improvement was, so I'm just gonna, did it it must have panicked before. Yeah, okay. So we're just going to stash what we have here, right? Let's just kind of go back in. And so basically this is failing if line is empty. I just want to double check this is doing what I expect. And okay. Okay, so we want to copy this code to use it, and then we're going to go back in here, pop the stash, so now we get our changes back, except we want to apply this fix also. Did that work? Get stash. Get stash pop. Okay. Oh, I guess it did work, yeah, because we just popped it on top. So yeah, we're mmapping, we're doing the decimal stuff. Now I just want to double check this actually works. Also, another thing that we're doing is as we're going to add this, we're just doing a linear scan every time. So we probably want to switch to a tree as like one of the next things. So this is, that's going to be as I32. And then now this is actually going to be slightly different. So this average temp, we're going to basically cast it as F32 and then divide by 10.0 to kind of chop it down back to the right size, and then we're going to divide by the count. And so this should work also. We're going to have to wait on this first guy to finish though and double check it works. That's so ironic, it literally got to the end of the file and then immediately failed. Because I think because it does have a trailing new line at the end, the final element of the split is actually the empty byte slice. And so, of course, that failed here because there's nothing in that slice. So yeah, I'm curious to see what happens here. Oh yeah, I still have to make some minor fixes to the webcam thing. Because right now I don't know if I should just display all the objects that are detected, because I'm holding this is a LaCroix can right here. And it looks weird because it's cropping the can out from me. It does a really good job, surprisingly. But I'd imagine that'd be a little confusing sometimes. So yeah, I hope it doesn't crash. Like, let me know, fingers crossed, I'll last up there in your corner to the end of the video, but we'll see. And Cargo Bench should be running this as in release mode by default. Yeah, optimized. And then also I have another little trick up my sleeve. Actually, this would have been cool to see, compare the difference of the baseline, because I don't know if the compiler will vectorize this loop. Okay, maybe this might be slightly faster. But anyway, we're just telling, I guess it would be LVM, that we want to compile for this specific computer. So whatever extensions I have, I think I have CPU info. Yeah, this is the CPU I have, and so it has a good amount of stuff. AVX512 in particular. We might jump into some SIMD stuff later and see what we can do there. So anyway, if I go all the way back up here, this is a little annoying. Literally shaking the camera with my scrolling. Come on, come on. Okay, I can disconnect my mouse. We will actually go way faster. I got a lot of CPUs, I guess. Come on, buddy. Yeah, so it was 144 seconds, and it looks like it did find the empty line at the end, so we're going to need that fix going forward. So that's good to know. We can delete this for now, save a little bit of time. Whoops. And if we print this out, now we have all of this. Okay, and actually we have the next thing ready to test. So this first test was, I think, just mapping it, and then it failed. And then we have the integer stuff. Yeah. It'd be cool to have some kind of CI thing for this. That would work a little nicer instead of having to manually juggle this. It'd be cool to just be able to push and have it test that exact code and see how it works, but at least we'll have like a local log of how we do on time. And because this is just a list and it's appending it, we'll be able to see, like, this will always be sorted in like the order we wrote it in. And so it'd be cool if we have any regressions or if there's enough error that cause it to bounce back or something. But yeah, this is good. So this is going to be integer math. And who knows if this will work, because basically part of testing this, basically it compares that it's what it should be at the end, but if we made a mistake here, then obviously that's not going to work. And so now we're going to bench. Yep, okay. Didn't fail. So now it's benching. We can start on the next thing. And so what do we want to tackle next? We have the mmap stuff. That's good. We're doing this optimized parsing. Maybe I kind of like doing the text stuff here. So let's get into, what's it called? It's like memchr. I forgot what the actual function is for this. Where's the library call? It's like mmchr, maybe, something like that. No, this is like manual code for it. Oh, stir, maybe. Yes, okay. Cool, so this will already get us into SIMD a little bit, so I'm curious how much this is going to help. Basically what this library does is, if we look at, let's say, the implementation of split, right? It's probably some weird iterator thing, but basically it has to manually search through and find the next token, which right now we're applying this closure, and so hopefully optimization should inline this, but if it doesn't, it's going to have to call this whole function. And then even if that's the case, it's going to be hard for the optimizer to see it can vectorize this. And so basically what this crate does is it's going to let us do split a lot faster, because it's searching in parallel using the vector instructions of our CPU to find probably 16 bytes in parallel of our next thing here. So we're just going to have a loop here. And we have to, oh, and we're still running here. We're going to add this. Okay. I'm sure. And what does this return, actually? Let's go to the docs. I don't want the function. Or does this let us... Oh, nice. Okay. This is actually exactly what we want. Needle haystack. Perfect. Okay. Oh, and our code is totally broken. Ooh, look at this diff. So in this last one, oh, are we no longer negative 32.2? Oh, yeah. Because yeah, we multiply by 10. Actually, these ranges don't work at all. Okay, what have we modified so far? Just added memchr. So if we just undo this, okay. So actually, sorry guys, these need to be I16. Whoops, I16. I wonder if there'd be any performance advantage to parsing this as an I8, because at least these ranges are going to be smaller. It's only when we multiply by 10 that we're running into trouble. I16, who's an I64? Oh, here. So hard. I never type I16, so I always type 64 instead. Okay. This should work now. This is an I32. You know, just to be safe, these might be massive. I'm just going to make this an I64 just to make sure we don't overflow. And then these are going to have to get updated. I64, I64. Yeah, I wonder how much this floating point stuff is costing us before. Okay. Okay, Caro bench. Okay, now we can get started on this thing. So So we're going to have an infinite loop, and then above it, and we want to use the struct memchr new, and we're searching for, this is going to be the new line, and now we can actually just inline this to make it a little bit nicer, so we don't have to do this weird casting. Whoops, and then we can do 4, and we also need I for the last, no, that's sorry, that's only formatting. 4 line is empty. Oh, this only, I think it only gives us the, yeah, iterator. How is that implemented? No, these are auto traits. What am I doing? Iterator. Here we go. So it gives you the next position, which is annoying. So no idea if this is actually going to work. I guess if we mess up this, the parsing should fail immediately, so we should know right away. So we're going to get the line, which is going to be last pause to next pause, right? And so we want to skip the new lines. So we want to add 1. And we can create this with memchr editor. That's a little nicer. Last pause. Okay, so next pause starts at 0. We're going to assign that to the position we find +1. And so this is going to go to the end. And then the next time we're going to start from the beginning. And this is still messed up somehow. 239. Our math must be really weird here. It looks like these averages seem reasonable though. Like, so the actual answer, or the first one, I guess, should be 18.0. And it's not selecting the diff. So our averages are actually correct. It's the min and the max that are causing us trouble, I guess. So this should be 38.0. This is -3. Okay, so look, we're not doing the math somewhere where we should. That's weird because we divide here. Are all of these messed up still? 249. Oh, I hope we're not getting some kind of weird rounding. That would be really unfortunate. -184 for this one. Oh, yeah, something's totally wrong here. And so int is the first part before the dot, which, yeah, that's right. Temp int, and the decimal is just the decimal. Is this actually true? That I think they do only have, yeah. So this would be 5, this would be 1, right? This gets multiplied to 50, and so this becomes 51. And this can go up to, it could be like 99 is like a max or a min, right? Or 72, right? So this would be stored as 720, so we definitely need 16-bit range. However, that's very odd. This division doesn't just work on its own, you know? Average temp, which is what we add to every time. Yep. As I64, that's it. I wonder if we're getting some kind of wrapping here. Like if No, actually the average is correct. It's the min and the max that aren't. Yeah. Yeah, the average is A-okay. So what would that mean? Only some of these are wrong. 0.0. You know, as we were writing this, I wish we could just, actually we might want to parallelize next just to make this everything blanketly faster, so that way we can iterate and test a little bit faster here as well. I should have done that first. I just want to see if this works, honestly. Okay, good. This is going to be... cargo bench. Yeah, let's see if this works now. Because we are definitely dividing. I don't know if that was there in the last commit. Let me see. Oops. Yeah, I literally just made this repo as I finished it. So this latest commit, I wonder if this, no. We were dividing by 10 last time. And it looks like the parsing doesn't fail immediately, so that's good at least. That's just, that's still very strange that, maybe it's something to do with floating point precision. I guess we'll see if this works, guys, and then try to go from there. Because this average is going to be massive, right? Because if there's in the expected, right? If we just vim this, we search for equals. Okay, so there's 100 cities, right? And I'm not sure how long each line is, but this is what, 1, right? That's a billion? Yeah, that's a million. That's a billion. And so let's say we say each line is like 30 bytes, right? And there's 100 cities. That means there's going to be a lot of entries. Yeah. Yeah, we're probably going to have like 500,000 entries per weather thing. And so this poor I-64, if the temperature, let's say the temperature is usually high there, right? And so 500,000, let's say the average temperature is like 80, worst case, right? Okay, this is definitely in range for an I-64, actually. That should be fine. Huh. Yeah, I don't know why that wouldn't work like that. And this runtime is abysmal, so I'm thinking, oh, still doesn't work. Nice. We might just have to undo this and yeah, and come back later. Oh, sorry, I'm a moron, guys. I'm actually a moron. This is going to be the same. Min. We're just going to divide by 10. Max. Okay, I'm sure you guys were yelling at me in real time there. That was very bad. Okay, min, max, whoops, average. Okay, and then we can ditch these guys. Make it a little nicer, nice. Okay, so I'm confident this should work now. So, fix. I wonder how much it didn't print. Okay, it's still very slow. Good to know. So this should finally work. So we can start multi-threading this, maybe with something like Rayon. This is going to be interesting, though. So basically what I'm thinking there's going to be a couple. Actually, let's just hop in GIMP here, so I can kind of talk through what I'm thinking. Let's create a new thing. Yep. And let's draw. Okay. With a nice color. Nice black. Yeah, so basically, right, we have this massive file. And inside the file, there's a bunch of lines, right? So if we think that each line is here, right, and this is like New York or something, right? And then the temperature and stuff, and then each line is a new city. I'm sort of showing it like this because we have it in one-dimensional memory, even though it's sort of a 2D thing because there's lines and then text within the line. But the lines are different lengths, right? So we can't break this down, cleanly by just kind of selecting a random length. So basically what I'm thinking, let's say we're running on a machine with 4 threads, right? So what we're going to want to do is break the file in about 4 equal pieces, right? And basically we're going to want to give to thread 1, this can be thread 2, this is thread 3. But if you imagine it, if we just split basically based on the total length of the file, which is like 14 GB, right? This isn't going to work, right? Because it's very unlikely this split is going to land on the same part as where there's a line. So what I'm thinking is we want to do as much work on multiple cores as possible, right? But the problem is splitting is kind of a serial operation, right? Because we're deciding who gets to do what. So we could either do stuff with like global atomics and have each thread like chunk off its next piece, like whenever it's done with its piece of work, it'll just go to the next and the next. I think it'll be a little simpler just to establish who's doing what right at the beginning. And so basically what I'm thinking, we basically mmap the file, figure out its length, and then divide it up into these chunks, and then just move back this start point for this next thread to the nearest line. Basically, we just go backwards. We can also go forwards. It doesn't matter too much. Actually, let's go forward, because then we can use memchr again, actually. So basically, let me undo this. So in this one, right, we basically go to the next one here with memchr. And if there's a long line here, right, we have to go a lot of bytes, we go to a long one here. But the problem is the file's so massive compared to the amount of threads. Even after doing this operation, it should be very even as far as which thread is doing what. And so basically what I'm thinking is basically at the start we'll get the length, do this like skipping operation to find out where we should be, and then that will give us basically a vector of start positions for each thread of where to go. And then from there they can look at just their chunk and process it, and then we'll piece everything together at the end. So let's go back. This is still failing. 31.8. That's not good. Huh? Min, max, min, average, max, station name. Guys, this is very concerning. Huh. 21.5. Yeah, I'm really not sure what's going on, guys. It looks like, are any of these averages busted? Some of them are, okay. That almost tells me that shouldn't be true though, right? That's very odd. So we split by the dot. I'm still disappointed we're still stuck on this, guys. This is actually embarrassing. Split once, int decimal, int in, decimal, decimal, put it together. So this is the top, right? And so this should be negative 76 for the first one. And then if that fails, we're just going to print out line, right? And so this should fail immediately. And we Yeah, and so we're getting, the first one is 76. Let's just do 50. Getting 7.6. The next one, though, is... Okay, so we get -7. Let's just do the first 5 so we can see what's going on. Okay, so we get -7. Oh, we have to carry the sign for both. That's it. Okay. So... so when we're doing the math here, we want to do the math in terms of the absolute value, and then if the leading thing is negative, right? So like this temp int will be negative if it's like -7, then we'll make this mutable. We'll just say temp equals -temp, right? Otherwise, we end up messing with it too much. Okay, compiles, nice. We'll put this back. Fix parsing map, sure. And we'll let this run in the background. Okay, so we know our strategy as far as concurrency. So this will be interesting. Actually, I wonder if there's something that'll do this already. Or we could just spawn the threads manually. That would also work too. Actually, we might want to do that so we have better control. So this is going to be like split file, right? And this is going to be this is going to be data. There's just going to be a bunch of bytes. And this is going to return vector positions within that. So the first thing we're going to want to do and so the first one is always going to be 0, right? Because that is, we always have to start at the file. For I in, it's going to be 1 to num threads, right? Because we already handled 0. Yeah, we want to do something similar. Actually, start is going to be data.len. So the amount of, on average, data each thread, actually no, let's do the math like this. So this start point is basically going to be the chunk size of each thread, which is the total data divided the number of threads, times which thread we're on. And so we have the size. Now we have to double check it starts on a new line. So now we're going to do memchr. Just the basic one. And so our needle is going to be the classic and this is going to be start to the end of data. And so if we don't find it, we're just going to go to the end of the file. Unwrap or... And actually it's going to be data.len because this end... Yeah, this end is exclusive. Actually, no, this is going to be data.len plus... So it's weird because each thread, the index that we're going to add to pauses comes after a new line, but at the end of the file, no, actually at the end of the file we should find a new line. So this should never, be hit. Is that right? Oh no, the way we're going to find the end is... No, we should always hit a new line. I just kind of want to see if this code generally works. So yeah, once we have it, let's say 4. And then we'll just panic so we make sure we get the debugging. And we'll limit this for now. It'd be nice to have a command line flag where we can say just run anyway. Okay, so it looks like, yeah, these are the byte offsets it found. So this is like 10 gigs into the file. It was able to find another new line. Okay, yeah. So, yeah, we're able to split the file. We're going to also need num threads. Num threads. And we'll just assume we can always get the number of threads. Debug start. That's not right. Thread should be 16. What? Okay, so we go past here. Go to the 17th thing. So 0, 1, 2, 3, 4, 5, 6. And maybe it's this? Oh no, it's this. What? Oh, this why am I thinking num threads? That must be the number of active threads in the program. Okay, so we don't need this anymore. Num CPUs, yeah. It's funny though that it actually works like that, and I implemented it without even thinking. That's a good library. Why are you crying? Num. What is it called? Get. And I guess that's nice. It always returns you something. But yeah, it's weird how they use the non-null thing. He's like, obviously, like, who cares, right? Okay, so this looks like 32. It's splitting it up nicely. You can see it's an even step size of around 400 megabytes per thread, right? So we get the pauses. We can delete some of these debugs here. And okay. Okay, so we create a vec with 0, and now this is going to be the next character at the end, right? So we're basically going to have a function called thread that takes in the full file. And then we're going to have to find a way to merge these somehow. That's fine though. we're going to need the stations again, except we're only going to have to do the mmap stuff once. And we're basically going to copy, so we split the file, last pause, yep. Oh, and we're only going to have to sort at the end of when we put it back together. So for... do we join them in parallel? So we're going to spawn a thread. And we're going to have to, yep, basically collect it and then join. Okay, we do have to collect this. Except let me paste this before I lose it. Whoops, so this is going to be back of something that we're going to collect. Into iter.map. We're just going to assume we can join all of them. So this can be a vec processed station, which is a really dirty type. I don't like that. That's fine. Collect, yes. Yes, because this is empty. And we're going to go off thread with data. Actually, this is going to be more like for... we can just iterate manually. Unwrap or is going to be data.len. And we're going to have to split ownership of this. We could do a thread builder, but that's all right. We do this? No, that's fine. We can deref on the inside. Yep, okay, that's fine. So get usize. What do you mean? Usize, what are you crying about? Oh, and this now has to be arc because we're sharing ownership. Okay. Yep, or we unwrap. So yeah, we get our data. Now this memchr stuff should be correct still. This is going to be big cheating because I'm going to get to use all my CPUs. We can also, we're probably going to want to end up overriding this to use, I think, for the official thing. Oh, 32 core. Do I have 32? I do, okay. This will actually be an interesting comparison then. I wonder how, yeah, how we're going to do basically. So we have a split file. We have the thread. Oh, you gotta be kidding me. What's it? It's like arc. There's some thing of this that's better. Also, I think we can just ask for read access from mmap or something like that. Make mute. Check advise range. Remap. We don't want to flatten. We just want to read from this. Okay, actually this is a bad idea. We don't want to make an arc of the... We'll just make an arc of this, right? That'll make this a lot easier. Yep, and because we have deref, even though this is an arc of mmap, this operation just works. So that's good. We don't need this. This is going to be arc. Clone it every time for each thread. Oh no, sorry, this is still... Very odd. Why are you crying? Oh yeah, okay, because this implements deref. This should work. This should work. Yeah, I was just crying because of this. And we need to initialize all of this here. And we need to move the closure, yep. Okay, so now merge. Should know the types. Yep, okay, and this is going to be vec process station. Yeah, we're going to start whipping the profile route soon because I've sort of just been guided by intuition thus far. But yeah, this is where it's going to get interesting. Okay, so... yeah, it's actually going to be a similar process to this one, where basically we go through each thing and make a master list. We're also going to want to move to type like a map or a tree structure soon, but for now we'll just stick with this. Yeah, we'll have mute stations. And then for this is going to be like thread Okay. Except we don't want thread data. We want to find this in here. And name, what is this all going to be? Ooh, adding the averages is going to be a little weird. Okay, so if it's none, we're going to push onto... Actually, if it's not there, we take by ownership, right? So we can just push this directly. Otherwise, now we need to merge the two. Okay, and then if s.max is greater than station.max, station s. And then we increment. Yeah, so basically we combine all of these together. Vec process station, why are you crying? Oh, no, we want to return result. Nice to have some tests for this as well, but who cares? Yep, we don't need this anymore because we merged them. And yeah, we join the threads. Let's see. See if this immediately panics. Okay, nice. Okay, these indices are probably wrong. Yes, okay, because this new line is where it starts relative to start, right? So we need to do start plus new line plus 1. Okay, looks like it's running. So let me, ooh, and can you hear the fan spinning up? I'm gonna put this back so it'll make us commit. No idea if this is gonna work. Come on, baby, fingers crossed. Okay, so now if I'm actually doing things, it'll slow it down if I'm doing things on the computer. But, guys, we're already sub 10 minutes, or sub 10 seconds. I don't know, we're not even probably an hour into this. Haha, let's go. This is gonna be so fast. Okay. So, that was way faster than I thought. This is awesome. We're going to be able to iterate so rapidly here. And actually, we can just make this the else branch. Now it's going to run so quick. We'll make this the... Do it like this, right? So that if it is dirty... See, it's going to run so quick, we won't even realize it. Except it's not going to append to the file, right? So if we look at this, there should be no duplicates. Yeah, so we got from 138 all the way down to 8 with this new commit. And the cool thing is we can actually just show and see, oh, when we did first pass concurrency, that's what dropped the time significantly by about 32 times. Look at it. So yeah, we should also memadvise on this. I wonder if that'll have any kind of effect. So we want to like basically memadvise each subsection of the list here. So we'll just take in a reference to the thing. mmap. Let's move this over a touch. Advise range. Okay. So sequential. Ooh, this is actually, this is just gonna be 0. Yeah, and then we're basically going to push last to pause. And mmap that. We'll see how fast this is. Could not allocate memory. What? Is that on the line where we unwrap? 22? Maybe it doesn't like us. Let's not do this actually. Because the thing is, each thread is reading this in parallel, so we actually do want to tell the kernel that, hey, we're going to read this chunk sequentially, and at the same time read this chunk sequentially starting here. Let's just see what this does. If this fails, then it's also something funky. Okay, no, it doesn't fail. So yeah, actually, we'll just get rid of this for the time being. Okay, so we do the parsing. Probably the next thing is going to be tree stuff for sure. This should be decently optimized. Okay. Yeah, okay, it's about the same. This is going to be memadvise cargo bench. Cool. So yeah, we'll get that cranking. It's unfortunate we can't do that, but oh well. Okay, so how we're going to want to do tree stuff here. So let's think about that. Basically, we want to be able to search rapidly. So the first thing that comes to mind is just a hash map over the name. I wonder though, because we only have 100 things, log to, right, once we reach steady state after a little bit, it's still going to take about 6 tries to basically bump down the tree to find the one we want. So actually we should just use a hash map here. So split file, that's not going to change. Each thread is basically now going to return a hash map of the string name to the yep, and then this is going to be similar. This can take a vec of hash maps and return you just a hash map. Yeah, my Vim is messed up. It'll freeze like that from time to time. I gotta fix that. Yeah, look at that. It's terrible. Oh, I got it right. Nice. Oops, nope, we can't paste. And this iterator instead is going to be, we don't care about the name because it's also inside there. .find, this is going to be the same thing basically, right? Itermute, what else needs to be mutable? What? Station. Except instead of iterating, this is just going to be .get i.name. This is just going to be get s.name. And this will return the full station if it finds it. Okay, this should work now. This needs to change to string. And instead of searching, nice, now we can just do i.name equals name, get name. Actually, we can use... Actually, it should make a difference. That's going to be so rare. I was going to say we could use the entry API to basically either get or create a new entry to let us insert and place. Because basically we actually have to do two searches here, right? We have to search for the name to realize it's not there. And then when we insert, we also have to rehash again to find where it should go and then redo it. The problem is there's only 100 cities, right? So this code is only going to run 100 times. This is going to run like a bajillion times. So it would be a valid optimization, but we'll leave it to later because there's probably not a lot of savings to be had there. Name.clone. Is this an str? Yeah, because we parse it. Okay, does this compile? No, absolutely not. So thread data. Okay, does the thread should return, yep, the hash map. This type is wrong now. I love that you can just throw concurrency at a problem and it'll get faster when you can just split a file like this. Actually, what got me into this was there's a video I saw of this guy doing this in Python, and he was like, oh, you know, my Python's only 8 times slower than the Java guys because I use, you know, this parallel library in Python. And I was just like, oh, you know, that's great. So basically we're going to iter, actually we can into, and just, whoops, make this into a vec. This is now this, uses a tuple. Yeah, so we merge the stations. Yeah, so basically get rid of the name here, just so we get the raw thing, and then we sort it like how we did before. And why are you crying? Get mutt. And this is the same thing, get mutt. You know, round probably has some sort of thing like this for deduplicating stuff on its own. I'm not sure what it is. Okay, let's try this. So we were at what, like 8 seconds before, was it? I can hear it running 8.2. Okay, let's see how we are. Ooh. Wow, that just made it 4 times faster, guys. Okay, let's commit this for real. Use okay, we're getting very close to. Oh, I don't want to touch the computer as it's running. Okay, 2.7. I wonder how consistent this is. This would honestly be, we're getting close enough we might want to start using Criterion and perf. Okay, it seems pretty consistent though, because now we're not doing as much. I wonder though, how are we allocating? So obviously we allocate the file at the beginning, but I think this should be no allocate. Yeah. There should be no clones in steady state. Like obviously we need to clone the name to put it in, like as owned into the hash map. I wonder about this though, from now this, if we just start adding in more unsafe code, this will make it faster. Oh, actually a little bit, okay. Actually, I wonder if we can keep this safe. Okay, we don't want to do this actually. We're just going to leave it as bytes, right? This is split once. Oh, the problem is the char things are going to be super annoying. We should be able to do this all as SIMD. Okay, so yeah, this is fine. can just use this. Still need this for the iter. And this is going to be semicolon, line. Okay. So now name is going to become line. So this is going to be the beginning to this. This is going to be this plus 1 to the end. Now we can get rid of this. And then this is going to be basically the same for this. So we're going to memchr for a dot inside temp str. Actually, once we have this, all of the numbers should be the same, right? Yeah, we might not have to do any parsing at all, because this should always be 4 bytes. Yeah. Okay. So actually, we're gonna once we do this, this is gonna be basically, okay, we want to grab the last 4 characters, which are always going to be 1, 2, oh no, that doesn't work actually. Actually, no, we're not going to do that. We're just going to basically rewrite the same code, but with memchr instead, that's fine. So yeah, we search for the dot in here. This first one, temp int, temp des, in semi-pause. And we're going to need our own parsing function. You know, I wonder how much. I wonder if someone has a small parser. There's probably a nice library we can use. This looks interesting though. I'll have to read this at some point. Not close. There has to be some kind of library for this though, right? This one got merged though. Interesting. Yeah, we could just from str unsafe. Actually, yeah, let's just do from str unsafe. This is going to be yeah, well, let's just use this alias everywhere to make it more clear what's going on. And we don't need this anymore. This stays the same. Name. We don't want a pretty print. Okay, let's keep this as a string and we'll just do unsafe name here. Actually, this is going to be so much faster, it almost doesn't even matter. From UTF-8. And we can just do the setup here just to make this a little bit nicer, like what we do for everything else, so this doesn't get too long. How are we doing? Bad. All right. Nice. Okay, so get the line. The name is everything before this. That's right. This is semi-pause. The string is everything after that. Yep. Then here, temp string, which is this. We search for the dot. Oh, all the threads are panicking. That's funny. Semi-pause. That's right. Oh, this is going to be dot. But oh, this isn't line. This is... Yeah, because it was just sub-slicing in the wrong thing, basically. Yeah, let's see what happens. Hard to tell. That's faster. 2.4. What was the best we had here? 2.7. Okay, that's a little bit faster. That's fine. Let's commit this. There we go. Cool. Oh, nice. We can even do this. Yeah, so we went all the way down from 152 to 2.5. Oh, I love how this is sequential. Yeah, we've literally made it faster every single time, guys. So yeah, this is pretty good. I'm trying to think what else we can do. Yeah, really, these are all like the high-level things I could think of off the top of my head. It gets problematic where now we need data in order to improve, because right, I don't actually know what's going on here. I'm just trying to see if there's any other thing that sticks out to me that we could do better on, but it's somewhat unlikely. Also, these hash maps we can create with capacity, right? Actually, that's a small change. Let's add a Criterion support, and then I'll... Can't go in parallel. Yeah, okay. Yeah, let's add Criterion support, and then we'll do... Yeah, okay. So the Criterion is going to look kind of similar to this, except we're not actually counting the... What's it called? We're not actually making sure that it works, but cargo test will verify that. Except we need to run in release mode, so we're not slow. Oh, this is our dummy thing. We can just make another one. can never spell or pronounce this, so we're just going to copy paste. Okay. So now we have to do this. Actually, we'll do this first. Dev dependencies, this is C. Yeah, then we can try out this and see if it makes it faster. So we added this. Now we need another bench. And we can just erase this real quick. All right, this is tough work. I had to get another LaCroix. So we have our new benchmark thingy. It's compiling it. Oops. Yeah, let's just put in their example for now. Okay, bench. Cool. Okay. So we're going to want to change this. We do want black box. And it's going to look something like this. Yeah, we can just copy this whole thing for now. So this is going to be, we want to cut down anything that's in here, right? Because anything that's in here is going to be counted. So we are going to include the time for formatting results because I think that's important. Yeah, we need black box for this for sure. We don't need to read expected either, or have this path. Okay. This is going to be benches 1 billion lines. Okay, so it says this takes about 12 microseconds. I wonder what it'll say now. Because the problem is it takes, if it's going to warm up for 3 seconds, it can only run one benchmark, right? Oh no, it's going to want to... We're going to have to change that for sure. This is going to be... I saw somewhere there was a comment. Okay, yep. C dot. Oh, that doesn't exist anymore. Nice. This takes self, but we don't have access to self. Oh, that's frustrating. Wait, what was it called? Sample measurement time. Okay, we definitely want to change sample size. Yep. The problem is we've figured out how to get access to self. So there's probably, yeah. So we have to create the group explicitly, I guess. Even though we already have a group, presumably, right? Because this main benches, billion lines. Okay, this can be bench. And we don't need this killing my computer while we're recording too. I'm gonna have to test this without recording as like the final number, because that's surely using up some CPU. Nice. Okay, now we have it. Okay. Okay, it has to be more than 10. And so this should be, I guess it doesn't describe sample size, but I'm assuming sample size is literally just however many times it does it. Fib 20, where did that come from? Oh. Yeah, okay, so for 10 samples it sees it's going to take about 25 seconds. That makes sense. I don't like how this is grouped. Okay, we'll stick with this naming because it has to be consistent if we're going to iterate with it. Yeah, and so as we kind of drill into the things that yield smaller results, because we've already chopped down the time a lot, there might be some we might not be able to tell if it actually makes it faster, and that's okay. It's a little annoying, but it just means it's not significant enough for us to track. But we will know if we do actually make it worse enough that it's like it can tell it's gotten worse. So yeah, we should be able to rely on that. Okay, 2.5. This region is pretty tight as well, so I'm feeling good about that. Okay, so let's commit this. Oop. It's going to use both. That's all right. That's fine. That'll be our official numbers, and we can start cranking. Actually, I don't want to touch it now that it's multi-threaded. Come on. Okay, good. No performance change detected. Nice. And it saved our new result. That's good. And the result is, yeah, within the confidence interval. This is actually a little fast. That's interesting. Oh well. As long as we have like just kind of like a ballpark, right, of what happened at each time. These are basically the same, right? And that's okay. So yeah, let's go to lib, and I forgot what the thing I was saying was. Yeah, so this is our hot loop here. There was something we were going to try. I forgot what it was. Using memchr iter for everything. Let's use that other crate. Whatever it's called. Why am I still... Oh, I guess our CPU is just hot. It's not actually being used a lot. So there was that crate I found. What was it called? This. Let's look this guy up. Hopefully there's a lot of stars, because this might already be merged in the standard library. Oh, no, we definitely don't care about this. Why is this here? I think David Tolnay has one, yeah. Oh, that's only for writing. Yeah, we don't want to format, we want to parse. Parse, what are we parsing? Yeah, okay, it's already been merged, so. Yeah, I think we can just stick with these. If anything, we're only going to get benefits, I think, if we end up using SIMD, which is going to get a little complicated. So let's start digging into some of the perf stuff. And I don't remember how to do this at all, so this will be interesting. This for Rust C, nope. Hopefully they have something for Criterion. That'll be interesting. Nope, that's not working, okay. I wonder if you can just use flamegraph. That might be the easiest idea. Okay. I hope this somehow goes to perf. No. I guess it will slow us down to do that, unfortunately. Huh. I wonder how much overhead there is for this. That'll be interesting. Yeah, I mean, this looks easy to work with, so we might as well just do this. This is dev only. What's it called so we can keep it alphabetical? P. I think that comes after S. Yeah, we're using that. That's fine. Okay. Active profiler, frequency. Interesting. I wonder if this will save it all to the file. Or no, I think we want this to be reused. Yeah, okay. So yeah, we need this custom thing. Put it at the bottom, this out of the way. Is there another crate I missed here too? Oh, he put this in a separate file. Okay, that's fine. We'll just put it at the bottom here. Is this the frequency? Probably gonna want it to be higher than that because we're gonna lose some. How fast is this though? Frequency is this. This probably just hurts, right? IE6. That's microseconds, so yeah, that's probably reasonable. Let's crank it up just slightly. Yeah, and then we're gonna have to override this guy. I think that goes. Okay. Bench function, which is here. We're gonna use this, and we have to use here. And we have to add Criterion macro. That's fine. No features? Okay, nice. That's annoying. Okay, I guess we gotta switch to nightly now, guys. That might change our performance slightly. Yeah, I think stable's my default here, yep. Rest up. There we go. Okay. Yeah, we'll get nightly from today. That's good. Hopefully this Rust C is nice and fast for us. There's no weird regressions. Recompile. Yep, new compiler. Nice. And why are you crying? So here they do the custom thing. Oh, so you can do it like this. Okay, yeah, we shouldn't need this anymore. Oh, maybe we can do this without the feature. Yeah, it'll be nice and easy. Okay, main targets equals bench. Okay, now we don't need this garbage or this. We don't need this. We don't need this. Crank this up. Huh? What did I mess up? Ah, that goes there. Yep, and then this goes away because it's right here. Alright, let's see what happens. Yeah, I wonder how much this will slow things down. Yeah, okay. Looks like they do the same thing. I wonder... pprof. Okay, this looks like literally the exact same thing. So we can get rid of this code, probably. Yep, that's what it looks like. Yeah, and then they just do, with profiler, this. That guy failed, but that's fine. What does this take? Flamegraph options. Where does this come from? That's annoying. Yeah, let's just see if we can do this without. I wonder how this will actually work. And let's crank this up. Just Criterion. And is there another feature for this? There probably is. Let's see. Flamegraph. Huh. That's weird. Did they remove this? Maybe? Oh yeah, okay, it does need a feature. Interesting. bring this back then. That's annoying. What? Yeah, we definitely want this feature. Are you kidding me? Where is this in the cargo.toml? Optional true, okay. And the example, okay, gives the features, I see. Oh, so features, yeah, this should be fine. I don't know why this is crying. And this is 0.5. pprof. Oh. Oh, this is really old, guys. That's not going to do it. 0.13. Okay, this should work now. There we go. Ooh. I like this. I hope this gets merged soon. This is sick. Ah, and then this must be like it's too soon, but there's some other dependency that has a minimum requirement, so it can't solve for this. That's really cool, actually. I love that. Yeah. Okay, well, it looks like the estimated time is still similar. So the overhead of this profiling shouldn't be too massive, hopefully. Let's see, though. No change. Nice. I wonder what it did with this thing, though. We're going to have to take a look at this. Stop profiling. Yeah, build flamegraph. Right. Default options. Yeah, I'm actually baffled where this is. How is it not in here? Maybe it's in a separate crate. Oh, yeah, we don't care about this stuff. This should be fine. And we ran Criterion, which is this one. So, why didn't that work? Huh. We do the sample size, yeah. This path is fine. That's weird. Maybe it's somewhere... this would be under bench, right? Yeah, that's not good, guys. Yeah, we should be able to find this file pretty easily. I don't know why I can't. GitHub's not letting me copy it. Yeah, it's not here. That's not good. Huh. What? This article was kind of garbage, but let's see what it says. Okay. We probably have to do this. He's setting profile time. That should be fine. Okay, it should be in profile. Oh yeah, so probably we can't get events, and that's why it's failing. Yeah, so if I rerun this and wait 30 seconds. Yeah, so he's doing this. We don't need that. It should show up in here because we enabled this. Yeah, okay. Yeah, let's see. Oh, the problem is, oh, this flamegraph is going to be terrible because it's basically we're doing everything. This inner loop is so fast. Let's see if it. No, okay, it's still not there. Yeah, actually, what we don't want is a flamegraph. This is a side quest that did nothing. What we do want, if I hopefully I can make this go away. That's really frustrating, guys. Yeah, we literally never wanted this. Okay, so let's rerun it just to show that we didn't do anything. Yeah, so what we actually care about is a perf report where we can see what percentage, like at each level in the call stack, what percent of the time is spent on each instruction and each function. So we need to do raw dog perf. Yes, okay, this is exactly what we want. Okay, we're gonna have to have debug info. That's a little annoying. Fair enough, though. Okay, no major changes detected. That's good. We're still chilling. Let's see. Yeah, okay, this is all about the same. 2.5. Wonder why it's longer. I guess the warm-up helps, like, because then the file can get in the kernel's cache. Yeah, that's probably it. Okay. So actually we need, let's just run this as a program. Yeah, and then we're literally gonna perf. Yeah, okay. So it's literally going to be the same as this test, right? Because this is like an entry point, but for the test. Fn main pub. We don't care about the time because we're going to do that manually. Time taken, we don't care. We want a pretty print. And we're just going to move this to a separate function so it's easy to see what's what in the report. Because we do want to check it to make sure if we break something, we know. But also we don't want this to end up confusing us. And so this solution returns what? Solution. Yeah, this is, okay, this is vec. Yeah, and then we literally just print it out. Okay. Out, format results. I don't know why I don't have IntelliSense. Oh, okay. Here we go. Yep. I wonder why that made it fail suddenly, though, instead of it just working. Fetching. Okay, scan roots. Nice. Yeah, we want to use the LSP to import all this stuff, so I don't do it manually. Yep. Now some of these have to become real dependencies, at least the pretty. Yeah, at least pretty assertions is going to become a regular dependency, as well as this is just going to be ob thing solution. Solution. Actually, we'll just import. No, we'll make it explicit. That's fine. STD path. Oh, and we do want to. Whoops. These expected. Yeah, we're just gonna copy all of this. Okay. It's running. Cool. Yeah, now we should be able to do perf record. Make this one command. Ooh, we need perf. So CLI. We really only want this. How big is perf? We really only want this on battle station. Yeah, OBS. Okay, we'll resync this. Hopefully that should just work. Home machines, battle station. No, it's not home though. Whoops. Yep, okay. With packages, we got to search here for perf. Ooh, yeah, we need to figure out which CPU we are. So 6.6. Oh, we might have to reboot actually if we're changing the kernel. That would make sense. Yep. Battle station. Module packages. Yeah, actually, let me just try it here and see what happens. Please work. LibrePerf. Oh yeah, I guess AMD probably has to provide it. Okay, I guess this still is Zen. Hold on. We probably want this one then. System packages. Yep. Yeah, we definitely want the one from the CPU manufacturer. Yeah, I wonder what this one would give us then. Because maybe this does pull in the correct one actually. Let me look at the source here. Source. Nice, it is flamegraph too. You can't escape. It's like, it's funny when you see the problem approached like from a different direction, but the same thing. Yeah, okay, it's doing make stuff. Nice. Okay, that worked. Cool. Yeah, and this is my auto streaming thing increasing this, so we'll only add this. And it's only on my desktop, which is kind of nice. Okay, so I can just basically steal this. Target, release, main. Huh. 15 millibytes of data. Okay, we probably care. I know the kernel will be interesting because that'll, when we're hitting the page fault, we'll be able to see if the kernel, if we're I/O bound or not. So, but this is interesting. Hopefully this article gets into, I forgot the, whoops. Yeah, there's some nice command for viewing it. Okay. All right, here we go. Ooh, okay. So it looks like parsing is taking a while. And we're spending a lot of time in memchr, which is good. And hashing. Yeah, I wonder if there's... if we can... Yeah, this is... I forgot what it is, but there's a perf view I like better. Perf report. Here we go. Oops. Yeah, so we should definitely try like FxHash or some like other unsafe hashing algorithm. So main, looks like a lot of this gets inlined as well, so it's tough to see what's going on. So yeah, we're doing a lot of hashing, a lot of scanning. Actually, really just parsing integers is the hardest hit thing right now. Yeah, so maybe then what we can do, what do we change? We don't need this anymore. What is it? pprof. We're just going to do Criterion, I guess. Source bin, we want to add this. Perf.data, we want to add this to getignore. Yeah, let's just make sure this is reasonable. Windows. What are we doing with Windows? Whatever. Yep, more benches, okay. And the main, okay. Add main for perf benchmarking. Let's do another run and just kind of see where we're at. Things that might have changed with the nightly compiler, so that'll be somewhat interesting. And yeah, it looks like we definitely want to use FxHash here. I don't want to touch anything though and mess up the benchmark, so we'll just wait here patiently. But yeah, hopefully this is interesting so far. I really love digging in, like this is some of the work I enjoy the most, of just sitting there and like optimizing the hell out of something. It's so much more fun because you can see over time, you know, how much progress you've made, and it's always really satisfying. And there's almost like an infinite amount of value you can extract, right? Like it's always a log curve where, you know, once we switched to multi-threading and that increased our speed up by 32 times, right? So you can only do that once, and then all the little steps after that are going to be smaller, but you can almost always improve somewhere, and so I just love that. Okay, it's good. It detected no difference, so that's good. It seems like perf's actually working. So yeah, let's switch to yeah, we're spending a lot of time hashing. I think it's called FxHash was the one. Ooh, REST performance book, interesting. Yeah, we don't care anything about hash DOS. We don't want to use a hash. We literally just want to use like raw dog hash for the keys. We should be able to implement that ourselves actually. I think that'll be most interesting is if we do that. So yeah, we're basically just going to override this type and then put in our own hasher. This is still going to be generic over KV. It's going to be generic over my hasher. Is it because I want to implement the trait? Oh, it probably because this has to implement default. Oh, so hashmap new. What info block is this in? Random state. So it has a new. Oh, we have to implement build hasher. Okay. It's just this, right? Okay, so we're going to assume our hash map is always name oops. Yeah, so these go here now. And now we don't want anyone writing generics since we type this out explicitly. New hash map. Actually, this becomes unambiguous. Or maybe it doesn't. Someone's still crying. This isn't good. Here we go. Oh, it's interesting that works, but the other one doesn't. We also want to do this. There's only 100 cities, so we probably want that. This is going to be this has to be pub. Okay. Okay, nice. We're using that now. That's good. So now this is going to be the name. I know there's some longer names in here. I just want to get an idea of like what's going on. Okay. Yeah, so literally the hash, this is going to be a very easy hash. Oh, it's annoying we can't just extend this. Oh, we can just copy this into this and do it. So we're going to do Okay, so we have the state already. We're only going to hash one thing at a time. So it starts out at 0. We're going to do as from raw parts mute star and there's 8 bytes in there, right? Yep, so now we have that as bytes. Copy from slice. And this is going to be self.state. What? Oh. If it's less. Yeah, we'll do whatever's smaller. So then this is the right size when we copy into it. Yep. And we'll set up the pointer here just to make it nice and easy. And right is 0. What does that even mean? So why would this be called multiple times, right? These should all be names, right? What? Sometimes they are. That's interesting. 5. Is there a city that... No, that's binary. There's no way. Okay, what if... I don't think we need this. Oh, we have to make this copy look. This has to be len as well. Come on. Is this slower? Why is this taking so long? Oh, because we're debugging. Yeah, no, we don't want any of that. That seems slower. Okay, let's run both and see what happens. I'm gonna get another drink real quick. Yeah, it seems like this definitely got slower somehow. I wonder why. Ooh. That's very baffling. It must be something to do with the fact that these numbers are different. Like, we could just read... Rust really wouldn't like that. Yeah, let's try this out with perf. Okay. I almost want to show like by instruction. I had a good perf command a while ago that was like exactly my defaults, but I'm not sure what happened to it. Oh, okay, this is what we want. Expand. Same as plus, okay. So yeah, mostly what we care about is this thread. So it's searching, parsing takes the most amount of time. Yep. Move copying. What are we copying? It's interesting because the hashing no longer shows up. Yeah, I wonder if we just do like an unsafe pointer read that's like insanely unsafe. Like if we literally just make a slice. Like undefined behavior, I feel like is totally fair game for this, like, if I'm gonna be honest. So yeah, we get pointer. It's always gonna be 8 bytes. We don't even need. Oh, yeah. So it doesn't need to be mutable. This is gonna be as pointer. No. It's going to be a star const u64 pointer.cast, and we're just going to XOR that with and it might be unaligned, so we have to read that unaligned, of course. This goes out of bounds, so it's 100% unsafe. We do this. I like being explicit. Okay. Oops, we need to rerun. And this fails. Interesting. I'm glad we added that check. It's weird though. I wouldn't expect these temperatures to fail. Oh, this hashing is non-deterministic now because we're we're reading random crap. So it must be inserting extra cities that don't exist. Is that what's happening? No, it looks like just numbers that are messed up. Okay, yeah, I think this whole thing was a failed endeavor. I'm going to commit this just so we have a baseline. We got to handle all of these. Okay. Does that include perf data itself? It does. Nice. Failed. Could also be that, oh yes, this hashing, The first one where we did correctly was probably only because it was XOR. I actually want to maybe get back to this. Yeah, so... yeah, let's bring this back actually, and we can just XOR each thing. Actually, we can make this... nice, now we don't need unsafe stuff. So we're going to do state sub I mod 8. XORed with B. Yeah, I think we were having a ton of collisions, which is probably why it didn't like this. So I wonder... what is it called? OBRC. Yeah, okay. Yeah, let's see what happens. It's still slower. Interesting. Yeah, I did not expect that at all. What else could have gone wrong since then? Like, I'm genuinely baffled. We might have to revert all this, guys. Okay, where did my tab go? Okay, we definitely want to try the parsing now, if we can. What do I call this? Oh, yeah. Yeah, so we almost want to revert. Okay, let's just bench this really fast. Cat. Yeah, the last couple have just been garbage. Alright, so let's revert. So the last one that was fast was this 9A thing, which is this one. So we want to revert these. Huh? Oh. This would be in order. Conflicts. No, we don't want conflicts. This should be completely gone. What? Oh. Okay. Yeah, so AB... yeah, everything with use custom hasher we want to get rid of. So let's revert this to head. Should be clean. Yep, okay. And we want to squash these. Okay, whatever. We don't need to squash it. Why do we still have this hasher thing, though? That's not good. So we revert. Okay. So we want to revert all of these and commit bench. So commit bench, safe hash still slow, failed hash experiment. Oh, we want to do custom hasher as well. Oh, it must have been something with the range. There we go. Okay. All right. Okay, this is fine. Let's just double check, sanity check. This should be fine. Cool. And it should have added that to the results. Nice. And let's see what perf is up to now. Okay. All right, so we're not going thread. Oh, we don't have a source for this? Are you kidding me? Hashing takes up a little bit of time, but it's all parsing. Okay. The bottleneck is totally parsing. So how can we make parsing faster? I think honestly just write out a simple inline version, because we know a couple things about this, right? Right, if I just look at it a little bit. So this is either, I wonder if there's any that are 0 point something. But okay, so this first digit here, it's either, it's basically 0 through 2 digits, and then there's this. I believe always, right? And so we should be able to write an inline version that at max reads 4 characters. Or sorry, I mean not inline, I mean where we already unroll the loop. Okay, and so I think it should always return an I16, yep. Okay, now we don't have to do temp int. Yep, this is just going to return the correct thing for us. We don't have to search for the dot, so that's going to eliminate a call to memchr. That's going to be good. This is going to be parsed fixed point, right? And this will handle this if it's negative. Yep. Equals this has to be character. Okay, so if neg okay, and let's write some tests for this as well. If we could parse with SIMD, that would be really great. So that's going to be 0. 1.0, this is going to be 10. If we get like 1, 5, 15, negative 25.3, 253, except negative. If we get, I guess who cares about like -0 edge cases, that's fine. There we go. Okay. So we checked this, right? So R, we're going to add to R the first digit we can find. Which could, so if we want to consume this, if it's R plus equals 0. Oh, whoops, what did I do? R, what type is this now? Okay, so we check that. If the number there if it's not the dot, we're basically going to do it again. And then after every step, we're basically going to do R times equals 10. And then pause. So at most we can have 2 digits here, right? So if you think about this test, let's think about this test case first. And we're going to want to do okay, so this first thing is working. We parse the first digit. I'm going to move this up here as the first one. Okay, so we're getting 25 already. That's good. So at most we're going to have 2 digits here and then the dot, right? So if it's not a dot, it means the next one should be the dot. So now the numpause should be the dot. We don't need to consume the dot. Okay, and then now we just parse the last digit. That works, okay. I don't know how resilient this is. This seems too simple to work. But yeah, let's just swipe it in and see if it works. I guess we already did implement it here. Criterion. Yeah, this will let us know if it's actually faster. This will be interesting. Oh, but shoot, the other one's going to fail. That might mess it up. Let's run just Criterion. Come on. Nice. There we go. We're sub 2 seconds, baby. Okay, and then let's just save this number for us. Yay! Alright, yeah, and let's see what perf is up to. Perf. I wonder where this instruction is, or where we're copying stuff. Thing is, do we beat Java? That's that's the real important thing. No, we need to beat Java. Oh, okay, we need, what, 25% improvement to beat Java? These guys they're probably doing something crazy though. Let's see. Cursor. Also, there's a good shot that the CPU that you're using, even though it has the same number of cores, it probably is more cache or something that makes it faster. So I'd have to actually submit mine and see what it does. Spawn worker. Huh. Oh, maybe it looks like it does 3 in parallel. It's like partially unrolled. And then this looks. Okay. Yeah, they basically unrolled everything and they do it in parallel. And they're using, what is this? They're doing pointer stuff directly. Oh, they're reading from the input. Yeah. Yep. Okay. Ooh. I have no idea what this is doing, guys. This is crazy. Unit digits. Huh. Yeah, but this will probably make it faster. And what do they use? A hashmap? Yeah, they just do a raw table. What is this hash though? Word 2. Okay, this is doing, yeah, it's almost like it's like SIMD, but for 64-bit registers where they're doing mass stuff. I feel like the way to actually make this faster, because we have access to this in Rust, and we're using Nightly already, would be to actually use SIMD, because we're still, yeah, we're most, whoops. Yeah, we're most bottlenecked. Yeah, but it looks like by hashing. I wonder if I just bring in FxHashMap, if that'll fix anything. Or maybe it's SIPHash? I forget, what is it called? Not cryptographically secure. Okay, that's right. Yeah. Size hash 64. Yeah, I think they probably use this function internally. They have the state. Right 32. Hash word. That's where all the business happens, it looks like. Oh, okay. So then I wonder if, okay, let's just try this. I wonder what will happen. It'll be really weird though if this actually makes it faster than the super unsafe implementation I had. That wouldn't make any sense to me. Okay, and then we should just be able to replace this with this. Okay, FxHashMap. I guess that's a private import, maybe. Huh? All right. Let's see if this is faster. Whoops, let's run just Criterion. It's a lot faster. Oh, oh, guys, do we beat Java? We need to beat Java. That's my one goal. One, okay. 535. Yes! Let's go! I'm still confused then. Why that's faster? Okay, so what's our bottleneck now then? Let's see. Where is that? Okay. Hash brown. Get mutt. Okay. So hitting the hash map is the slowest part. I wonder though, I'm sure we can do some kind of weird analysis on the results. Not measurements. Expected out. Actually, this will be easier in main. Out. Yeah. So names is just going to be okay. Do a pretty print. Where does this go before? I'm confused. Yeah, okay. Except from UTF-8. to owned. Okay. Give me all the names. Nice. Yeah, I bet we could find some kind of like simple idealized hashing algorithm that we can literally take like the first 2 characters or something really stupid, and then we can just ditch all the hashmap stuff. Maybe 3 characters. What is the shortest length here? I'm curious. I'm going to say 4 characters. Names. The min's 3. Okay. I wonder if there's any that conflict. So the way we can check that. I think we can collect into a hash set, right? This goes here. Yep. Please don't panic. Ooh. We don't want to do string stuff. Yeah, actually this doesn't need to be UTF-8 at all. There's that many places, really? I guess a lot of them do conflict even at 3 characters. Okay, well, I'm going to call it here, guys. That was a ton of fun. We ended up beating Java in the end. This can definitely be optimized a lot more. I have 2 things in mind. Basically, some kind of custom hash algorithm that uses the knowledge of this. Basically, our input space is only this, right, instead of the full spectrum of all the possible bytes. And so if we can eliminate collisions and have a really fast algorithm, we can basically map that directly to an index, like have our own hash map, right, except know that we don't have collisions, which simplifies the equality checking and everything, right? So I'm going to take a look at that offline, see if I can improve that. Also, there's an awesome C++ library called SIMD JSON, which somehow is able to parse JSON with SIMD, or at least parts of JSON with SIMD. I think it's arrays or something like that. And so kind of like what we were looking at with the Java code, where it's basically running everything. Yeah, basically they unroll this, like 3 iterations of the loop, and try to find 3 in parallel. SIMD this is almost like SIMD except manual, right? Except in here you would write it once and then it would run on multiple pieces of data. And we'd be able to scale this past just 3 items at a time. We'd be able to do 4 or maybe even 16 depending on the instructions we want to use and the registers and all that. So that's another big one too that we can use to optimize. So yeah, stick around. There should be another episode coming out soon. Yeah, and there's going to be some more speedrunning C coming out soon. I just got another assignment for that. So yeah, peace out.